So now here we have the Lamberts Law, which is used in ultraviolet and visible spectroscopy to determine concentrations that are related to our drugs, because most of the drugs absorb light in the UV spectrum, in the ultraviolet, and there are very few that absorb light in the visible spectrum. So, Mr. Lee, it's your time to shine.
So here we have your Lamberts Law with a formula of this log intensity of incident light and intensity of transmitted light. Here is absorbance and molar extinction coefficient. This is your path length in cm, usually 1 cm, and your concentration in molars or moles per liter. This will be your Beer's law, and this will be your Lamberts law.
So these are actually two separate formulas, but we combined it into one. So it's actually like this. So one is the absorbance equals your logarithm of IO over IT, and the other one is this. Your absorbance is basically your molar extinction coefficient times the B and C. So these are two different formulas.
And here we have an illustration of how the intensity of incident light will be absorbed. And this will be your percent absorbance. And we have another formula here for percent absorbance. Do not confuse it with absorbance because it is a different thing. Here we have the intensity of incident light and transmitted light subtracted together to get your percent absorbance. Well, this one is just a constant, 100.
It's always 100.
100%. And here we have another formula for pharmaceutical drug products of Lamberts law. Here is concentration and your A11 value, absorbance divided by 100. And this should be your units.
Your final answer will be in grams per 100 ml. Never forget that there's an invisible 100 ml right there at the bottom.
And it's here.
And when you divide it by 100, the answer you'll get is grams per ml, because you already divided it by 100. Your answer should actually be smaller.
So here we have another sample problem where your absorbance is equal to 2%. Absorbance is being solved for. So first, what we do here is we have to get your IT. And how would we do this? Simply use the Lamberts law here, and we can further break this down into antilog A.
So basically, antilog is just 10 raised to something. So if you have, let's say, the number 2, the antilog of 2 is just 10 raised to 2. It's just the beauty of math.
So here we have 100 over antilog 2. And your answer should be 1%. However, what we're asked to look for is percent absorbance.
Yeah, it's not.
And not IT.
Yeah.
So we use this formula over here. Minus 1. So your final answer should be 99%.
See, these two can be very confusing. Never interchange these two. A is actually different from percent A. Percent A is how much light your drug actually absorbed out of 100%.
So here is another sample problem where we are given the A11 value of 557 at 291 nanometers and absorbance.
The wavelength is usually pretty useless. Like, it's given at 291, given at 300. You can ignore these values. You should always focus at, for example, your A11 is this, A11 is that.
Yeah, so we have a sample problem here which says, what are the concentrations of the following solutions of drugs in grams per 100 ml and milligrams per 100 ml? So given is the drug carbimazole with A11 value of 517 here, 557, and absorbance here. So simply we use this formula here.
Yep, pretty easy. When we have these formulas in pharmacy, it's most of the time we just plug in the values. The real challenge is knowing which value is which, because sometimes they use very confusing words.
So here we have absorbance of 0.557. Plug in your 557. Here is 100. So if you're asked to look for grams per 100 ml, you do not divide 100. You simply get this value
Per 100 ml.
here. But if you're asked for milligrams per 100 ml, you don't need to touch the denominator, but simply just change it, convert it.
That's 1
milligram.
And yeah, when you have it grams per 100 ml, it's the same as percent weight per volume, because percent weight per volume is grams per 100 your grams per 100 ml. So when you're asked to get the percent weight per volume, it's the same thing. You just write 0.001%.
And for our last sample problem, we have here given the concentration of solution in a 1 centimeter cell and percent absorbance of 8.08%.
So the whole problem is actually at 200 nanometers, a 5 times 10 to the negative 14 molar solution of a compound was measured in a 1 centimeter cell. It was absorbed at 8.08%, and you have to calculate number 1, the wavelength. So this is where we get to use all our formulas. And I think in our exam, this is the one they're gonna give because it includes most of the formulas in one problem.
Yeah, so simply here in our wavelengths, if you're asked to get the wavelength in angstrom, simply convert your 200 nanometer given here.
1 nanometer is actually 10 angstroms. It's a unit used with proteins because proteins are pretty small molecules there and stuff. I learned it in biochem. It's been a long time. 1 nm is 10 angstrom. Okay, so we just had a little bit issue here. So 1 nanometer is just 10 angstroms. So if you're given 200 nanometers, it's just 2000 angstroms. So a very simple question. I don't think they're gonna ask that. It's too simple.
This one's for frequency. Just use your formula over here. A constant of 3 times 10 raised to 8 and your wavelength. Given wavelength over here, 200 nanometers.
So you just divide both and you will get
1.5 times 10 to the 15 per second.
Is it negative 15 or positive 15?
It's positive.
Okay.
And here, use this formula.
Yeah, to calculate for...
Or simply, you can use this. E equals HV. Plug in your frequency value. Over here, you'll get 4.93. I'm sorry, it's 9.93 times 10 to the negative 12.
So yeah, you guys do the calculation, we'll just write the answers and explain it.
But this would be in ergs.
Yep, it was actually asked in a different unit. So 1 joule is actually...
1 joule is actually
9.9.
10 raised to 7 ergs.
Okay, 1 times 10 raised to 7. So yeah, you just have to memorize these constants because apparently they don't like giving constants. They want you to work hard for things you'll eventually forget.
And next, for the absorbance of the solution,
which is your A, and it's different from 8%.
And your given is percent absorbance. So you cannot directly plug in your value 8.08% as your answer. So now we have to subtract again from this formula 100 minus 8.08%. So you get 91.92%.
Yeah, if you want to go from percent A to A, first you need to get your transmitted percent of your transmitted light, because if you remember, in order to get A, you need IT, and I always 100. We already have it. So yeah, that's why you need your IT first, which you can just subtract 100 from your percent absorbance, so you can see here, and there you have it. And then you use the formula to get A.
Yeah, and our next formula would be...
Yeah, that's the simplest part. You just plug in your calculator.
And this one would be from here, derived here.
And the answer you'll get is?
0.0366.
Yeah, pretty simple. And lastly,
If you're asked to solve for the molar extinction coefficient of the compound, simply use here this formula. Just get and derive.
here A, we calculated it here.
From here, calculated
366, and then
your wavelength, usually 1 cm, as
your B.
we mentioned
Your B.
earlier.
It's that wavelength. C.
Yeah.
And your C is
Sorry.
a constant. B is also a constant. So there are a lot of constants here you want to memorize.
Yeah. So don't forget, molar could also be in moles per liter.
Yeah, because our C here is actually in molars. When here our C is actually grams per 100 ml. So they really want to confuse us with different units. They love confusing people.
So here, the answer you should get is 73.2 liters per mole times cm from the units here.
Yep, CM, just different units. Okay, that's it.